Hi, today I'm going to talk about the policy gradient, which is basically a policy-based reinforcement learning algorithm, different from the value-based RL algorithm that we covered in the last videos. So, first of all, unlike the value-based reinforcement learning, policy-based RL approximates, for example, if it was a neural network, it constructs a neural network explicitly to calculate the policies, which is the action that would be chosen in a particular time step, instead of using the medium of a value network or an action value network. So first of all, in the previous value-based reinforcement learning, the policy was implicit. We didn't explicitly set a function approximator for it, which was, for example, it was epsilon greedy or greedy. It was more of an implicit policy form. But now we directly parameterize the policy using, say, a neural network or another sort of value function approximator. And one more thing to note is that this is still on model-free reinforcement learning, which means that we learn by directly interacting with the environment instead of calculating and speculating what would happen if we chose this pair of action in this state. So this is the basic Venn diagram for the value-based reinforcement learning algorithm and the policy-based reinforcement learning algorithms. So as you can see, in the middle, the intersection, there's a thing called the actor-critic reinforcement learning, which we will cover later. And it's basically using both value function approximator and the policy approximator. So why do we spare to do this policy-based reinforcement learning? It's because, first of all, I have mentioned that in the value-based models, the policies were rather implicit. It was epsilon greedy or greedy, which was an excellent choice given some form of value functions. But the disadvantage of it was that by that form, we couldn't really learn stochastic policies. We could only learn deterministic policies with that. Despite that, in the epsilon greedy, we did allow some randomness by the epsilon itself, but given the convergent theory, the epsilon had to, by the time steps advances, the epsilon had to decrease to the limit of 0. So the first advantage of policy-based reinforcement learning is that we could learn stochastic policies. And also, since we're directly parameterizing the policies, we don't have to suffer from such abrupt changes in the value function, the values of the action value or value functions, which means that it has a better convergence behavior. And also another advantage is that it's also effective in the continuous action spaces. So I mentioned that the policy-based reinforcement learning can learn stochastic policies. So which kind of situations would this property shine? For example, when we're playing rock, scissors, paper, then if our policy was deterministic, then it would, for example, if the opponent was keep on throwing rocks, then if our policy was greedy, then we would train on acting with the paper, because paper dominates rock. But if we are too trained to only throwing out papers, then the opponent will catch that pattern and just switch to return acting with giving out scissors, which means that then we would have to train again to that particular pattern again. So this is an example where a stochastic policy, which we throw out rock, paper, or scissor with 33% each, is the optimal policy for that domain. So that's one example where it shines. And another example where the stochastic policy is beneficial is when we are in a partially observed MDP. So we know that there was a theorem that the greedy policy always leads to the optimal policies. We covered that theorem before, but that was only for the full MDP. When we know we know completely about the environment, which is basically the state transition function and the reward function. But in partially observed MDPs, such theorem does not hold anymore, which means that state aliasing can occur, which is that to the agent, two or three or more distinct states are considered to be exactly the same because of the insufficient information about the environment itself. Because we don't fully know about the environment, we lack the ability to differentiate between some states, which naturally leads to state aliasing. And also, this state aliasing issue doesn't only come from the insufficient information. It also comes from when we're approximating the value function with a function approximator. For example, if we are using a linear combination of feature function approximator for the value, then we would have to come up with some kind of informative features. But there could be cases that the features that were chosen by us do not really represent the MDP full enough, which is equivalent to a situation where we have an insufficient information of the MDP. So that could also lead to state aliasing. So specifically, as a specific example, if you can see here, this is the alias grid word example, which means that these dark states are considered to be state alias. Basically means that the agent cannot differentiate between the two states, because for the other white three states, the agent can differentiate because the adjacent states are either the gold or the skeleton, and also between these two states in the end, there's also a difference, because for the leftmost state, the left and the north and the west are covered with a wall, but for the rightmost state, the north and the east is covered with a wall. So there's a difference. The agent can catch this, which leads to a different value function, which will then be applied to the implicit greedy or epsilon greedy approach, which one it is. And so it could ultimately lead to the best state, the terminal state, which is here the gold. But the problem is that with the value-based approach, these two states, the dark states, cannot be differentiated with the given features because both states are blocked north and south. And so there's a symmetry here, which inhibits the agent from differentiating differentiating these two states, which leads to the same value function. And if in that case, if the agent acts deterministically, for these states, it will go either to the left, both to the left, or both to the right. But we already know that for the white states, these arrows are the given optimal behavior. And for example, if the agent initiated started in the dark left state, then there would be an infinite loop over here. It would first advance to the west, east, so it will never converge. So this shows the disadvantage of using a value-based approach, why, given that it's a partially observed MDP. So the policy-based approach is an option, a choice to go in this kind of situations, because it's directly parameterizing the policy. We no longer have to follow the greedy or epsilon greedy policy anymore. So we have freedom to set the optimal policy, or we could actually use the randomness, the stochasticness in the policy by specifying for this two dark states is there's a 50-50 probability of going to the west or the east, which will more easily and deterministically converge to the terminal state in this example. So since we're using a policy-based approach instead of the value-based approach, in the value-based approach, basically for convergence, we use a gradient descent to minimize the objective function, which was the mean squared error between the value, the estimated value, and the true value. So since we are trying to minimize the error, we had to use the stochastic gradient descent. But for the policy-based approach, now we want to know the objective function is different here. We no longer want to minimize some kind of error function, but we want to maximize the expected value of a policy. So now instead of the gradient descent, we're going with the gradient ascent, which graphically we're given a surface of objective function, and we're trying to figure out the highest point, the maximum point. And in the graph, in the 3D graph, then it doesn't have to be a 3D, but let's just assume that we are, if we have two parameters, because again, this policy objective function is training the parameters based on the stochastic ascent algorithm. So in this case, we're trying to train the theta, the parameters. So how would we measure the quality of a policy, which is based on theta? There could be three approaches, which, for example, if we are given an episodic environment, which means that there's clearly a terminal state in the episode. In that case, we could use the start value of each state, which, because in the environment, there will be multiple states, a number of states, and starting from, say, state 1 to the terminal state, there will be a value function for that state 1. And from state 2, there will be a terminal state, there will be a value function until onwards to the terminal state as well, right? So we are basically just getting we're based on the start value of such state. We are calculating the quality of a policy. That's the idea of the first approach. And for the second approach, we could also just get the average of the environment. And this average value approach is mostly used in continuing environments where there's no such start state or no terminal state. In reinforcement learning, there a lot of environments like that. So more formally, it's getting the just getting the expected value based on the stationary distribution of the Markov chain based on some policy. We're averaging out with the value functions per each state, which makes the average value across all the states. And that's the second approach. And the third approach is just confining ourselves, because the second approach we are trying to average out until the terminal state starting from one state. But instead of just accounting for all the time steps, we will try to just account for one time step, which is same to the second approach, but now we are trying to average out of the immediate rewards for a one time step across different for the policy, given the state distribution. So that's the third approach. And the advantage of the policy-based reinforcement learning is that the policy gradient for all of these three objective functions turn out to be the same. So it doesn't really matter which, in terms of the policy gradient, it doesn't really matter which objective function we chose. So, okay, so when we try to optimize the policy, until just now, I just talked about the approaches that have the gradient-based approaches. But in optimization, there's also gradient-free approaches for like genetic algorithms or simplex. But if in cases that we can compute the gradient, it's more practical to go with those gradient-based approaches because there is more efficient, and we can also exploit the sequential structure. I mean, if we were trying to go with a genetic algorithm, then we would have to wait until the end of the episode, and at the end of the episode, it will be returned, this is the value of this episode, and then we would have to apply the algorithm to the next episode. And so, in other words, we would have to wait until one episode to improve such policy. But with the gradient approach, we don't necessarily have to do that. We could improve our policy during the lifetime of the environment, the learning environment. So that's what exactly means that we're exploiting the sequential structure. So I have emphasized that this time we're using the gradient ascent. And again, same, so except for that we're using ascent instead of descent, all the policy gradient and the concepts are the same. Again, here we are also, in terms of updating the weights, we're also introducing a stable size parameter, which is basically a learning rate, which was same from the value, which is exactly what we did in the value-based approach. And also, when we try to compute the policy gradient, of course, the most formal and intuitive way is to compute all the partial derivatives of the objective function with respect to each parameter, which is a vector of those is basically a policy gradient. But there are cases that we can't differentiate the objective functions, that we don't know how to. There can be those kind of cases. So in that case, we could compute the gradients using the finite differences, which is for each parameter, we perturb the weight by a small amount. And then that's the approximation of the partial derivative of the objective function with respect to the parameter. So that's the way, but because we're just, okay, so what we're basically doing in this finite difference approach is that we are calculating the objective function of the weight perturbed and get the difference with the original objective function, and we scale it with the perturbation, the error term that we just introduced. So that's a very simple approach, but it's very inefficient and noisy because we are using the perturbation. We're introducing some noise there. But this is certainly not a way to go when the policy is differentiable explicitly. But in some cases where the policy cannot be differentiated, or when we don't know how to differentiate the policy, this finite difference approach could be considered. And just as a short introduction, the aibo, the Japanese robot, which has a task to move faster, which is the maximization function is to move faster, use this finite difference approach because there were only 12 parameters, and in that case it worked well. But it's certainly a very non-analytic way to compute the gradient, so it's not very recommendable. So if you want to calculate the policy gradient analytically, let's first assume that the policy is differentiable, because now otherwise we would have to use finite difference, but in this case, let's say that it's differentiable. Okay, so what we want to know is we want to know the gradient of the policy, because we want to climb up the surface of the objective function. That's exactly what the gradients will tell us in terms of maximizing the objective function of a certain policy. And here we could introduce and we would also want to know the expected value of that gradient, which is very hard to tackle in the beginning. So we would have to introduce a likelihood ratio trick, which is basically the gradient of the policy is, first of all, obviously equal to the policy times the division of the gradient of the policy by the policy itself. And in that second term, the gradient of the policy divided by the policy is same as the gradient of the log of the policy, which is simple calculus, because if you try to calculate the derivative of the log gradient with respect to the policy, because it would become 1 over policy times the gradient of the policy because of the chain rule. And this second term, which is also called the score function, appears a lot in statistics or machine learning. And the reason for doing this kind of trick is because this score function term is the gradient that we would want to follow to maximize the log likelihood of that action. So this term, in other words, is what maximizes the log likelihood. And also one more advantage is that I mentioned that you wanted to get the expected value of the gradient of the policy, but to do that directly was difficult. But now, since it's represented as another term, it's easy to get the expected value, because it's basically the resulting term is the policy times the score function, and the policy is based on probability, so it's it's now a piece of cake to apply the expected expectation. So specifically, what kind of policies are we interested in? So first of all, if you are dealing with, if the action space was discrete, we could consider using the softmax policy, which when the term softmax is used, we're basically exponentiating something and normalizing to express it into a percentage, percentage per each entity, here action. So in this case, the term that we are trying to exponentiate, it might be the linear combination of features, which is basically the dot product of the feature vector and the weight vector. So so in other words, we're computing the probability of action, which is proportional to the exponentiated weight of the feature vectors, okay? And this, for example, in the previous example that I talked about, the rock, scissors, paper, if we follow the greedy policy, then it might not make sense in the rock, scissors, paper, right? So by using the softmax policy, because the action space of the rock, scissors, paper is discrete, it's either rock, scissors, or paper, 3 discrete actions. And if we follow the softmax policy, action of rock would have 33.3%, scissors, and so 33.3, and for paper as well. So in that case, it's basically became a stochastic policy, which is desirable in that specific domain, right? So this softmax policy would be used in those kind of situations. And so I would like to again emphasize that the score function of the policy gradient is basically the gradient that we would want to follow to maximize the log likelihood of some action, which was told by the policy. So in this softmax policy, that score function is equivalent to the feature subtraction of the feature to the expected feature, which means that the first feature is based on the action that was actually selected, and the second term is the expected feature. So it's basically represents the surprise, like what was the real difference between the expected feature and the actual selected feature, which is basically equivalent to the score function used, which is a gradient to follow to maximize that specific action in the medium of the feature in this case. So that was for the score function for the softmax policy. And when the action space is continuous, we will not go with cannot go with the softmax policy because it's for discrete actions. We would instead have to go with the Gaussian policy, which is basically exploiting the normal distribution. So when it comes to like the Gaussian distribution, we would have to be interested in the mean and the variance term, right? And in this case, the mean might be the linear combination of the state features again, as we did just right before. And the variance could be fixed or also could be parameterized, but the main idea is that the action is mostly, so the action is being drawn from a normal distribution of the continuous action space. So most of the time, the action that's chosen would be the mean action with the most probability density, but sometimes with some variance, which could be parameterized or not parameterized, we would also draw some random actions as well based on the probability distribution. So the gist of this Gaussian policy is also that we are using we are also trying to implement the stochasticness, the randomness. We're trying to implement the randomness, which is also an advantage in the policy-based approach. And in this case, the score function is also the idea is similar to what we did for the score function for the softmax policy, which is here the score function for a Gaussian policy is the subtraction of the actual action chosen with the mean action multiplied by the feature scaled by and then scaled by the variance, which the idea is exactly the same as in the softmax policy score function. So then how would we actually compute the MDP? How would we actually compute the policy gradient instead of approximating as we did in the two previous policies? So we could give an example. First, approach this with an example of a one-step MDP, which one-step MDP is just that we start with some arbitrary state and we just make one action, and then the next state is a terminal state. So it's just the time step is 1. So in this case, our objective function would be the reward, the immediate reward, which could be the objective function is the expectation of the immediate reward, which could be expanded as the product of the stationary distribution of the states with the random reward based on the given policy. So that's and our interest is to calculate the gradient of that objective function to figure out how we could maximize the log likelihood of this action A. Would we want to reinforce it, or would we want to make the occurrence less is solely based on what happens to be the actual reward in this case? So more simply in other words, the gradient of the objective function is the probability times the score function times the reward. And that was for the one-step MDP, which led to us considering the reward. But if it was a multi-step MDP, that reward term could be substituted by the action value function or the value function, which primarily means that instead of considering that one-step reward, we want to consider the accumulative rewards until it hits the terminal step, or estimation of the steps after the first reward time step. And in this case, also in the policy gradient term, now the policy gradient term could be expressed as the expected value based on the policy distribution of the score function multiplied by the action value function itself. And this policy gradient is uniform across the 3 objective functions, which I introduced previously, which was the first one was the start value, second one was the average reward based on one time step, the third was the average value. So the policy gradient is uniform for these 3 scenarios. Okay. And with this policy gradient theorem, it also, because we want to, we could also introduce a Monte Carlo method here, because anyway, we would want to, this last value function here, this is a true value function, which I said, okay, to again introduce, the policy gradient is the expected value of the score function multiplied by the true value function. This true value function could typically represents the true action value function, but it could be another value function. It doesn't matter. But this true value function is impossible to get unless we are in a supervised learning setting, but this is a reinforcement learning setting. So we would have to calculate or estimate this true value function in another kind of method. And one of the method could be the Monte Carlo method, or another method could be a TD or a TD lambda. But first, to combine it with the Monte Carlo method, we are now the policy gradient function includes the Monte Carlo return, which is basically the unbiased but very noisy return that we just throw the dice. We just make the agent actually interact with the environment until this terminal state, and that terminal state would give the actual return, but very high variance. And in that case, then we could utilize that Monte Carlo method to implement the reinforced function, which is a very prototype function. So the idea is to just initialize the weights arbitrarily when we start. And then we, as the Monte Carlo method does, we just gather all the rewards. We just make the agent run by itself until the end. So that will lead to an actual reward vector. And then based on those actual rewards, we calculate the value, which a value returned value is basically at time step t, the sum of all the rewards from starting from t at time step t plus 1. The value would be the sums of the rewards starting from time steps t plus 1. So that's the idea. So, and we're utilizing that value in adjusting our weight vector combined with the learning rate alpha. It's a very simple idea. And okay, so if we implement this Monte Carlo policy gradient, it does have a very smooth learning curve, which is desirable. But the problem is that it is high variance given of course, the Monte Carlo method is itself very high variance. And also it takes too long to converge. So we would want to improve this approach by making the by reducing the variance and also making the learning process shorter, faster. So first, let's tackle how to reduce the high variance. To reduce the high variance, we could use a concept of critic. So now we are introducing an actor-critic policy gradient, which is basically using both. So yes, I introduced this concept before. The actor-critic reinforcement learning is the intersection of the value-based approach and the policy-based approach. So it's using both policy gradients and the value function approximator. And so in this actor-critic, the actor is for the policy. Actor chooses the action to pick in each time step, and the critic is, as the name suggests, it's calculating whatever the value function is, Q value or advantage, is calculating the quality of that action that the actor made. So the critic is basically approximating the true value function. And both, if you think it as in two neural network form, now we're using two neural networks. One is the actor neural network, the second one, the critic neural network, and both are simultaneously updating their own weights. And then the natural question is, how do they communicate to each other? The way that they communicate to each other is it through the policy gradient equation, which we know that the policy gradient of this policy gradient is the expected value of the score function times the value function, approximate value function, right? So the value function here is approximated by the critic network. So that's where these two distinct actor and the critic meets. And also, since we don't know the true action value, which is estimated by the critic, we would have to use a policy evaluation approach again, which we could either use a Monte Carlo policy evaluation, TD learning policy evaluation, or TD lambda, or also the least squares policy evaluation that we covered in the last video. So specifically, if we would like to go over the pseudocode for the action value actor critic policy gradient algorithm. Okay, so let's just assume that we are calculating the estimated action value using a linear combination of features. Then the Q value, estimated Q value, would be the dot product of the weight vector and the feature vector. And okay, so that's the input. And the pseudocode for this whole approach would be we first initialize the state and the parameters, and we sample some arbitrary reaction based on our random policy. This is a random policy because the parameters, the theta is arbitrary as well. So for each step, we would sample reward and the transition, the next state, and also sample an action based on our current policy. Then based on that, we would calculate our Behrman error, which is basically the difference between the immediate reward plus the discounted the action value onwards from the next state. The difference with the current action value, that makes the Behrman error. And then we use that Behrman error in updating the weight of our the critic network, the critic part. We're using that to update our critic weights, and our actor weights would be again updated using that estimated Q value, but now it's a different equation, which the update of the actor weights is basically comprised of the multiplication of the learning rate times the score function times the value action value function. So we're doing that in one single loop step until we converge. So that was the pseudocode. And this approach, which we approximate the Q value instead of running to the end as we did in the Monte Carlo, it obviously introduced some bias. Remember that the Monte Carlo method is very high variance but has no bias. But now this approach reduces a lot of variance, but now introduces a lot of bias, because specifically here we implemented the naive TD, which is only based on one real interaction. So again, to tackle this bias problem, we could utilize what we did before, the TD lambda, which is mixing across different timescales. That could be an alternative. And one thing to note is that there's also another way to make this policy gradient Okay, so just to wrap things up, the first question from here should be, since we are using an estimation of the action value and plugging that in into the policy gradient calculation, then wouldn't that lead some bias in the policy gradient itself? That's a natural question that we should have. But there's a leeway, there's a way to avoid that occurrence of the bias. And it is to avoid that, there should be two conditions to satisfy, which is that the value function approximator should be compatible to the policy. In other words, the score function should be equal to the gradient of the Q value, the action value function. That's the first property to satisfy. And the second property to satisfy is the value function parameters should minimize the mean squared error. So if those two properties are satisfied, then despite that we estimated the action value function instead of using the true action value function, our policy gradient could have zero bias. It could be exact based on those two properties, which is kind of a surprise. So the formal proof for that surprise is given here, and the thing to take from here is that we could just directly substitute the estimated action value into the policy gradient without introducing any bias to the policy gradient. And again, another way, so now our interest is to reduce the variance instead of the bias. The formal proof was that we could make zero bias out of this approach. And now, since we dealt with the bias, we would also want to deal with the variance issue, because still, even though TD0 is TD0 is much less lower variance compared to the Monte Carlo, it still has variance issues which could adversely, and unfortunately in some cases it could explode the algorithm. We would want to avoid that, and to reduce that variance factor, we could also use we could introduce a concept of using a baseline function. So what we would like to do is would like to subtract the baseline function from the policy gradient, and this doesn't. So the natural question is that if we subtract something from the policy gradient, then would our policy gradient, the direction, would it lead to the correct direction even after that subtraction? That would be a natural and obvious question for that approach. But it turns out to be intact. Such subtraction doesn't change the expectation of the policy gradient, which while reducing the variance, which is very desirable. And just a higher level idea is that the expected value of the score function multiplied by the baseline function will always be equal to 0, which prevents from changing the expectation of the policy gradient itself. So practically, in practice, what would the baseline function be? So the most intuitive and practical baseline function would be the state value function. So in that case, it would be equivalent for us subtracting the state value function from the action value function, which is basically would become the advantage function. So intuitively, we are now figuring out for some time, for some states S. From this state S, we would have some estimation of what would happen onwards, which is basically the value function for that state. And then the action value function for that state S and some arbitrary action A would be at that state S, we chose this action. Then what would be the estimation by choosing that action in this state S? That would be the action value. So the difference between the action value and the value would be proportional to the quality of making that action, which is just the right information that we would need to maximize the log likelihood of that action A. So that would naturally also lead to the correct direction in the policy gradient, even though we subtracted something from it. So now we know that the advantage function could reduce variance without changing the expectation. So then in this case, to calculate the advantage function, we know that we need the action value function and the state value function. So should we calculate everything in the same time? When it comes to neural networks, then we would have to have a value function of neural network, an action value function neural network, and we would have to subtract the resulting values from each of them. And that could be a choice, but it also introduces some space complexity because we would have to construct one more neural network with that approach, which is undesirable. So that could be also dealt with because it's also very interesting that the advantage function is in fact the estimate of a sample. So the TD error sample is basically the unbiased estimate of the advantage function, which means that if we can manage to calculate the TD error, then which is based on only the state value function, then we would not have to even have a approximator for the action value function, because formally the TD error of some policy is basically the difference between the immediate reward of taking some action and the discounted value function from the next state minus the value function of this state. And the first term there, if we get the expected value of it, then it becomes, the TD error is equivalent to the action value of the state action combination subtracted by the state value function of that state, which is equivalent further to the advantage function. So if we could calculate the TD error, then we don't have to bother, we don't have to calculate the action value function, which is, it means that if we only need one function approximator for the state value function, then we're all good. We could utilize all the advantage from using the advantage function. And also, since we can only use one set of critic parameters now, there's also ways to calculate the critics parameters. We could use the Monte Carlo TD, naive TD, but the best way is to kind of get the best trade-off between the two high bias, low variance, and high variance, low bias approaches, which is using the TD lambda. The TD lambda, and between TD lambda, the forward view, and the backward view is more beneficial because we could utilize we could apply the updates online to incomplete sequences. And the difference in the backward view TD lambda between the value-based approach and the policy-based approach is that in terms of the eligibility trace, the second term of the eligibility is instead of the gradient of the value function, now it's the score function. So we're keeping track of the scores for each state action pair, and then when we update the weights, we credit the high state and action pair scores for those state and action pairs. And here again, we're also using the discounted. We're also by time step, we're discounting the eligibility trace by the lambda term. So one more thing to note is that the stochastic, so what we have been talking until so far was that we are trying to start with some stochastic policy, and it really depends on which policy we choose, but the same thing is that we're trying to exploit the stochasticness, the randomness, so that we could solve problems, for example, like the rock scissor paper problem, as we talked about before. But this could have a disadvantage because we're sampling based on the randomness. We are tuning our weights based on the random action that we make, which we're narrowing down we're trying to converge based on such randomness. But this could also unfortunately lead to explosion of the algorithm itself. So as an alternative, we could modify our policy gradient. So the original policy gradient was the expected value of the score function multiplied by the action value function, and we could modify that policy gradient equation into the expected value of the score function multiplied by the gradient of the action value function, which this intuitively means that instead of just training our weights based on what turned out to be the best, which is by the medium of the action value function, we are also trying to converge to the direction where the action value function is higher, where the Q function is high, because the critic network, the critic already has information of the direction, which direction to advance to maximize the Q value. So instead of just stochastically randomly picking those, we're now trying to exploit it, which is now becomes a deterministic policy gradient instead of the stochastic policy gradient that we talked about before. And this this converges faster and also does not suffer from such algorithm explosion issues, and also scales up to it also has a scaling advantage. So this is a summary of the policy gradient algorithms. Okay, so there, as you can see here, there are variations, but the main idea is the same. The main idea is that we would like to tune our weights to the direction where the Q value, the likelihood of an action is maximized. if that action leads to a good value. So more or less, we are trying to reinforce, we are trying to make the frequency of the action that lead to good values increase, and we are trying to avoid actions that lead to lower action values. That's the main idea. And so for the policy for the actor part, what we're doing is basically the same, but there's some difference in terms of the critic part, which in the Monte Carlo policy gradient, we just calculate the value of the whole sequence until the terminal point. And in the, we could also just approximate the action value, or could do the advantage function or TD hour or backward TD lambda. That really is our choice. And here, these are all expressed in expected value, but if we wanted to apply the stochastic gradient ascent, then we could just drop all these expectation notations and just sample the inside term of this expectation term.